So the Lewis structure helped us figure out how many bonds we have within a molecule. Then we looked at Vesper, which helped us look at the shape. Intermolecular forces will help us understand not only how the shape of the molecule is, but how that shape will determine how it interacts with other molecules of different shapes or similar shapes. So when we're looking at this, we're going to look at the main question that you want to ask yourself. Is the item nonpolar or polar? That is the main question you're going to ask yourself. Is it nonpolar, which are going to have very different properties than something that is polar? So I guess the best example is nonpolar would be something like oil. Polar would be something like water. So anything that's water soluble is polar. Anything that's not water soluble will most likely be oil soluble, which will be nonpolar. So that's where we're going to have those two differences. And then we learned in the past soap is kind of both, right? Soap has a non-polar side and a polar side, and because of that, it can help mix oils and waters together, or oil and vinegar. So that's the main goal. When we're looking at intermolecular forces, we're asking ourselves whether it's polar or non-polar. So the first one is, let's do the diatomic molecules. So we have oxygen. So even though oxygen is very electronegative, these oxygens are equal. So they're going to pull on those electrons exactly the same. So if I drew it a little bit bigger, so we are talking about lone electrons and even bonds, but in reality, if these are oxygen molecules, sorry I didn't draw it the same size. If these are oxygen molecules, they have electrons floating around them randomly. Let me make sure I got that. 1, 2, 3, 4, 5, 6, 7, 8. Wait. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So let's just count that. 1, 2, 3, 4, 5, 6, 7, 8. All right, so now they're floating around them, but they're going to share two of them to kind of give them that full octet. So let's say they shared these two and these two. Now, notice I drew it like this on purpose because it doesn't have to always be like this. Okay, these electrons are kind of moving around, but this is the highest probability. And then the electrons around are probably like this. This is, again, the highest probability, but it could be anywhere within this cloud. So a lot of times if you ever look at pictures in textbooks and you looked at electron density, what it's going to show you is just clouds, not dots for electrons, but clouds. And that's kind of to hopefully show you that, okay, it's most likely in these areas. So we're going to have electrons around here, and then it'll be like denser here, okay, but it could also be out in the middle, okay. So because of that, it's going to be evenly spread. Now, again, these two are exactly the same thing. So this oxygen is going to pull on these pairs of electrons the same amount as this oxygen. So in the end, even though this is very electronegative, since they're pulling on each other, the net is 0. Okay. Now let's look at another one. CH4. So when we're looking at this, even though this is more electronegative, and the reason why we're looking at electronegativity, if it's more electronegative, that means it's going to take that shared electron closer to that molecule. And it makes sense. This carbon has 6 protons, hydrogen only has 1, so those 6 protons are going to have a harder pull or a stronger pull towards the carbon. So even though carbon is more electronegative, what happens is that since the hydrogens are equally spaced apart, they're all going to be pulled in the same amount, they're just going to cancel each other out. So even though, again, kind of like the oxygen, even though you have electronegativity with the oxygen, the pull cancel each other out. Here, the pull cancel each other out. So here again, the net is 0. And when the net is 0, it is non-polar. So let's look at another one. Where's my eraser? There it is. So normally in organic chemistry, when you have carbon, if I just covered this side, if I just got rid of this, if I had a carbon bonded with the oxygen, this is going to be polar because carbon is way less electronegative than oxygen. So what's going to happen? So let's just make it, oop. So let's say this is our group. What's going to happen is it's going to pull a lot toward that way. And remember, this is a plus, which means it's going to be more plus, and this is going to be more negative. It's going to pull this way. But this isn't the case in carbon dioxide. In carbon dioxide, it's not a carbon on this side. It's actually another oxygen. And because of that, both of these oxygens are going to pull at the same and opposite direction. So again, here the net is 0. So it's going to be non-polar. So when something is non-polar, the only interaction that it has is London dispersion force. And it's kind of weird again. So remember, if we look back to here, most likely these electrons are right here. Okay, but they can shift. You know, it could get closer to carbon, it could get closer to oxygen. It's random, remember? It's in a cloud itself. So what could happen is, instead of it equally distributed, so this is the ideal case. Let me draw the ideal case. The ideal case is, you have 1, 2, 3, 4, oxygen. 1, 2, 3, 4, oxygen. 1, 2, 1, 2, 1, 2, 1, 2. So this is the ideal case of it. But it could happen, even though they're pulling equally and the net is non-polar, what could happen is maybe, whoop, I should have done dots. Maybe this electron was shaded more that way. And because of that, now this electron might shade itself closer to carbon. And when that happens, you have a partially negative side and a partially positive side. And it's very, very slight. But that's why it's called London dispersion. It happens with non-polar stuff. So this is London dispersion, if I spelled that correctly, or LD. And this happens in non-polar molecules. And it's just because electrons, even though they should be there, there's a slight chance they could be around. And they could keep flipping back and forth really quickly. Now in polar, let's do PCl3. So phosphorus has 1, 2, 3, 4, 5. Chlorine has 1, 2, 3, 4, 5, 6, 7. If you look at the periodic table, here it is. You have phosphorus down here, like nitrogen, has 5. It is going to be less electronegative than chlorine. So chlorine is going to have a bigger pull on the electrons than phosphorus. So when we're looking at this 3D structure, it's going to look like this. Oop. P, then you're going to have lone pair chlorine, chlorine sticking out, chlorine going in. So what's going to happen is you're going to have a pull all this way. So the net dipole is going to be down. So all the chlorines are going to be more electronegative than the phosphorus. So it's going to pull, and even though they're pulling away, those cancel each other out, but the one that's pulling down is going to be the one that's going to give your net dipole. So here we don't have a net of equal to 0. It's actually a net that's equal to down, or at least in the way I drew it, down. And because of that, you're going to get a partially negative charge and then a partially positive charge on top because of that unequal sharing of electrons. So that's what we get. This is a polar substance that's going to make a dipole interaction. And the dipole means it's dual polarity. So dipole. So if you had another PCl3, P, Cl, Cl, Cl. What's going to happen is this side's going to be partially positive, this side's going to be partially negative, and they're going to arrange themselves. This is going to be more attracted to this side, right? And then this is not attracted to this, so they're going to push each other away. So they're going to arrange themselves where the positive and the negative end are going to be together. So this is something that's polar, and it's dipolar. Now, the other classic one is NH3, NH3. So when I draw it, it's going to look almost exactly the same as this one. So it's a pyramidal, it's a tetrahedral with a lone pair on top. Now the difference is here you have chlorines that are more electronegative. Here you have the nitrogen that's more electronegative. So it's going to pull all the electrons instead of down, it's going to pull all the electrons out. So my net is going to be up. Now the difference here is this is going to be a very special case. And the reason why it's a very special case is because of hydrogen. All hydrogen only has, if we look at the Lewis structure, hydrogen has no electrons. So when these shared electrons are getting pulled closer to the nitrogen, this becomes very positive and this becomes very negative. And because of that, remember, with nitrogen, oxygen, and fluorine, very electronegative molecules, you get to do something called hydrogen bonds. So instead of just a positive with a negative, it's still a positive and negative, but because hydrogen is so now naked, it has no electrons next to it, because it's being pulled away towards the nitrogen in the bond, it's very, very positive. So when it does interact with negative, it's a little bit stronger than just a normal dipole-dipole. So this is still a dipole-dipole, but it's going to be a hydrogen bond. So these are the differences between intermolecular forces. Here's the three: Lenglen dispersion, which is non-polar. Then you have two polar ones, which is dipole-dipole, and then the stronger version, which is hydrogen bond. This only can happen with nitrogen, oxygen, fluorine. With hydrogen, well, this one's just any polar substance.